Good evening, everyone. Welcome to this Royal Geographical Society event arranged by the West of England and South Wales Committee of the RGS, and tonight jointly with the BRLSI, the Bath Royal Literary and Scientific Institution. Our West of England Committee runs events program throughout the year. So next week, for example, on Wednesday, we have Professor Andy Tatum on COVID-19 and the geography of disease dynamics. And the following day, on Thursday, we have the Assistant Fire Chief for Avon, Rob Davis, who will be talking about his international search and rescue experiences from disasters in Haiti and through to the Beirut port explosion. So that's a bit of a mouthful then. So to tonight. Well, back in January, a friend of mine recommended I watch a talk by Dr. Luke Daly on meteors, meteorites, and the UK Fireball Alliance. So I did, and it was so enjoyable and so full of information that I watched it again and started to wonder if it was really possible to include this in a geographical program, as I assumed Luke was an astronomer. So I was delighted when I looked him up at Glasgow University and found he lectures at the Department of Geography and Earth Sciences. So he's a kindred spirit. He's a member of the geography tribe, as far as I'm concerned. So of course we could invite him. What we didn't know in January, of course, and none of us could have guessed, none of us would have known that a speedy messenger from deep time was, with impeccable timing, was coming our way and would arrive on a driveway in Gloucestershire, and that Luke would be directly involved. So what I'm now going to do is hand over to my colleague Dick Bateman at BRLSI, as this is our joint event. So over to you, Dick.
Thank you very much, Jeff, and thank you, Luke, for coming down. And watch out, because there are meteorites flying all around you here. Bath Royal Literary and Scientific Institution's been going since 1824, and one of our donations was a little bit from a meteorite that fell in Siberia. So I'm really delighted to see Razilia from Ekaterinburg in Russia. How apt. So our meteorite is a palisite, and we've also got in and very close to BRLSI, the world famous Herschel Society, and Tony Symes of the Herschel Society is with us tonight. So we'll definitely have some excellent questions. If I could just reiterate Helena's point, down to the bottom of share screen, you will see to the left chat. And if you're not sure about this, just click on it, and you can type a message in the bottom right-hand corner of the white screen that appears on the right-hand side of your screen. So type your message in, just enter, and it will come up, and we'll take questions from the first one written, and you can write during Luke's talk, so we'll take questions in order from them. And I will give you 5 seconds to unmute when I say your name. So if you're the first questioner, be ready after Luke's talk, and we'll go straight on to the question. It would be best if you, the questioner, is able to read out your question, but I'll give you 5 seconds, and if you don't cut in, I'll do it myself. You have been warned. Ladies and gentlemen, Dr. Luke Daly.
Thanks very much for having me. I guess I'll share my screen and get started. So I guess it's probably no secret the sort of significance of what just happened last week with the Winchcombe meteorite being recovered. I'm still getting my head around it and how crazy awesome it is. And so I've frantically rewritten this talk from what I normally give, which is normally a talk about how we're aiming to recover the first meteorite in the UK for 30 years. And it's now a talk about how we've recovered the first meteorite in the UK for 30 years. And this is kind of the story about UK Fireball Alliance, how it came to be. It's where I started with this whole project out in Australia, right up until literally just history happening right now with the Winchcombe meteorite being recovered. And the importance of camera networks imaging fireballs to find meteorites on the ground. So I can't seem to navigate my slides. Right, here we go. So first things first, what are meteorites? Meteorites are rocks from space, and they can be narrowed down to basically three main groups. There are the iron meteorites, which, as the name suggests, are made out of iron and nickel metal. These meteorites are really important to study to understand how our solar system formed, because they come from the cores of planets. When a planetary body gets big enough, the heat inside causes it to melt. All the heavy elements, particularly iron and nickel, sink down to the center, forming a core structure. So our Earth and all the planetary bodies in our solar system have a core mantle crust structure. Iron meteorites are really important to help us understand this sort of like the core of planets, particularly the core of our own planet, because we can't get samples of our own Earth's core because it's dark and deep and squishy and miserable and horrible down there. We just can't drill that deep. And so some poor planet early in our solar system's history got bust up, and fragments of it now rain down onto the Earth in the form of iron meteorites. And we can study the minerals and the chemistry and the isotopes inside them to understand how cores form and how our own core might look. Another group of meteorites is called the Stony Iron Meteorites. These, as the name suggests, are made of bits of stone and bits of iron. It used to be thought that they came from the core mantle boundary of planets, so that transition between the metal core and the silicate mantle. But some recent data and sort of recent insights have shown that potentially these don't represent core mantle boundary samples. They may represent some of the most cataclysmic events in our solar system. And that is when two protoplanets smash into each other. So the core of one planet merges and is injected into the mantle of another, causing this beautiful patchwork texture of metal embedded with silicate minerals. And then finally, we have the Stony Meteorites. They're split into two types. First, we have the Chondrites. And the Chondrite meteorites, they come from the crusts of planets, the surface of planets. So we have Chondrite meteorites from the moon, from Mars, from the asteroid Vesta. And by studying them, we can understand volcanic processes on other worlds. So volcanoes on Mars, volcanoes on the moon, but also how crust is created and destroyed through asteroid impacts. And then finally, my favorite meteorite group, and the meteorite group I spend most of my time studying, and what fell out of the sky on us a couple of weeks ago, are the chondrites. Now, the chondrites are really important because they are the oldest rocks in our solar system. They're the oldest rocks you'll ever hold in your hand. They're 4.5 billion years old. All the minerals, all the grains, all the crystals inside them formed within the first few million years of our solar system's history. So just when the sun first started to shine. And so we can study them they provide a window into that early period of our solar system before there were planets, when it was just the sun and a swirling disk of gas and dust. And then how do we bring those together to build a planetary system? A few notes on terminology, because I get some of these questions a lot. There are kind of three words that get confused: meteoroid, meteor, and meteorite. So I'll just go through what those are. A meteoroid is simply just a rock in space. So a meteoroid is just flying around in our solar system, nowhere near the Earth. A meteor is just the light in the sky. So when a meteoroid hits the top of the atmosphere, going at several kilometers a second, starts to slow down, burn up, its outer surface melts and turns into a plasma, generating that glow. And that light that you see, that is the meteor. If it's a particularly big meteoroid, that meteor could last for several seconds, could fragment, could burst. And that's when it starts being called a fireball. And those ones are really important for us because they have a higher likelihood of dropping meteorites at the end of that burning trail. And then once that meteoroid has fallen to the Earth, it becomes a meteorite. So the only difference between a meteoroid and a meteorite is it's hit the deck, it's on the Earth now. And I always wondered about when that transition happens in that definition. Like if you caught it, is it still a meteoroid? And then you drop it and it's a meteorite? Does it have to hit the ground or if it hits a roof? Like where does that change? But anyway, that's just sort of like what keeps me up at night. I'm not sure about anyone else. And then going forward, studying these meteorites basically starts getting us at some of the biggest questions in planetary science, namely, how do you build a solar system? How do you build planets? How do you build worlds that are nice enough for life to get going and get started? So kind of the key things we want to know by studying meteorites are, how do we go from a big ball of gas and dust before our sun formed? How do we collapse that down under its own gravity until the center of it has high enough pressure and high enough temperatures for nuclear fusion to get kick-started and give birth to a star? How does the swirling disk of gas and dust around that young sun come together to build bigger and bigger objects through asteroids to protoplanets to eventually having the planetary system we see in our solar system today with a third rock from the sun that has life on it that's arguably intelligent? And meteorites help us get at these big questions. There are other ways we can also do this, like there's amazing astronomy community using high-powered telescopes like the ALMAS telescope, beaming back images from planetary systems in our galaxy that are forming right now. So this image is from a protoplanetary disk around a young sun. This is a sort of real-time image. This is happening right now in our solar system. Sorry, not in our solar system, in our galaxy. And you can see this beautiful structure, this ring system where, and in those gaps between those rings, potentially we're seeing planetary systems forming and planets forming. We can also use telescopes to look at our own solar system and the asteroid belt and the distribution of asteroids and where things are and where things are going. So the sort of like near-Earth asteroid detection system from NASA is starting over the last few decades to keep track of all the objects that are in our local neighborhood. They're tracking over 100,000 objects. So our local neighborhood is really quite busy. We're tracking about over 95% of the stuff that's out there. And the good news is, none of it is coming anywhere near us, at least of any considerable size, in the next 100,000 years. So we're safe in terms of like Greenland, Armageddon, deep impact style things, but small things do get through. And that's what gives us sort of like these beautiful fireball events that drop little bits of space rock. However, what we want to do is be able to link these two disciplines, really. We want to link the astronomy community who are looking at asteroids in our solar system and link the meteorites that we have on Earth in our collections to the asteroids in space. Don't worry too much about these two diagrams. It's just kind of there to show you that the meteorite classification system and the asteroid classification system are both alphabet soups of hell. And what we really want to do is be able to link meteorites that we have on Earth to their asteroids in space. We can measure meteorites' chemistry, we can measure their minerals inside them, get an idea about what they're made of. And we can also look at asteroids, look at the light that gets reflected off them from the sun to have an idea about what they're made of as well. But we really want to bring those two together and figure out what meteorites represent, what meteorites come from what asteroid, because that is the only way to do sort of solar system geology, solar system geological histories. And because this is kind of such an important question, folks like NASA and the Japanese Space Agency are spending billions of pounds sending probes to these asteroids. So, for example, the Hayabusa mission was sent to an S-type asteroid called Itokawa, landed on it very briefly, picked up a few hundred particles from the surface of this asteroid and brought it safely back to the Earth. That was back in 2011, which is awesome. There was also the Stardust mission that flew through the tail of a comet using aerogel to capture some small dust particles from that cometary tail and bring them back to Earth for study. So we have an idea about what comets are made of. There's also two missions to water-rich asteroids, Ryugu and Bennu, from NASA's OSIRIS-REx mission and the Hayabusa 2 mission to Ryugu. The Ryugu mission actually came back in December, bringing with it about 5 grams of material, which is spectacular. And no list like this would be complete without mention of the big one, which was the Apollo missions, which brought back kilos and kilos of moon rock. And by studying those samples and knowing where they came from on the moon, we were able to really start understanding how our Earth-Moon system formed through the giant impact, and loads of wonderful science has come from that mission. I'd also like to show you this video just because it blows my mind every time. This is the Hayabusa 2 mission's touch and go maneuver onto the surface of the asteroid Ryugu. It's going down, it's going to shoot a tantalum bullet at the surface, which kicks up a load of dust. Some of that dust went up that new Hoover-like chute and into the sample container, and that has been safely delivered. We've got about 5 grams pristine from the surface of this asteroid for study around the world. It's currently safely in Sagamihara in Japan and will be distributed to scientists around the world, I think in June. And researchers in the UK are going to be working on this mission and working on these samples, including us here at Glasgow. We're going to get 3 whole particles, which is tiny, but also massively significant to study. And hopefully we're going to get some really nice data out of it. And what these missions allow us to do for the low price of one Neymar Jr., or about £250 million, is we are now able to link an S-type asteroid, the asteroid Itokawa, to Chondrite meteorites on Earth. So we measure the dust that was brought back by the Hayabusa mission, and it is a sort of exact match to the Chondrite meteorites we have on Earth. So we are now able to kind of, with relative certainty, say the Chondrite meteorites we have on Earth probably came from asteroids like Itokawa, these S-type asteroids. However, there is a slightly cheaper way to do this, because space falls out of the sky at us all the time. We have these beautiful fireball events. I'll just play that video again, which is a meteoroid entering our atmosphere, burning up, and then potentially dropping a meteorite at the end. And that's where stuff like, and we're very good at finding these meteorites. We're really good at finding them. However, most of the meteorites we find are just lying on the ground. We haven't seen them fall. A really good example of this is the Antarctic Search for Meteorites, which is an expedition that goes out to Antarctica every year. And that takes advantage of a couple of factors of the Antarctic environment and meteorites. The first thing is meteorites land on this glacier, and that glacier is moving, particularly when it comes up against mountain ranges. The winds ablate that ice away and basically suction all these rocks back up to the surface and concentrate them up against those ridges. And because you've concentrated all these meteorites, you can then take advantage of the second environmental factor, is that meteorites are little black rocks. And little black rocks on white ice stick out like a sore thumb. You can see these things from literally kilometers away. So these expeditions from ANSMET, but there's also the Japanese-led mission, the Belgian mission, and for the first time a few years back, the UK led its own mission to Antarctica to collect the lost meteorites from Antarctica, which was led out of Manchester with Katie Joy, to recover meteorites like this in Antarctica. And they bring back thousands every year, which is great for our science. So we have over 60,000 meteorites in worldwide collections, thanks to expeditions like this. However, they have one crucial piece of information missing. They're all missing their orbit. They're just fortuitous, serendipitous finds that we've picked up off the ground. We don't know where in the solar system they come from. And this is a problem because we're trying to do solar system geology. And for sort of by way of comparison, it's kind of like trying to reconstruct the geological history of the UK with 50,000 random rocks that are dumped in your backyard. And no one told you where they got them from. No one told you you've got all of them. You've just got a bunch of rocks and they're right, go try and tell us how the UK formed, how the UK came to be. It's doable, but it's very challenging. We would much prefer to know where those rocks came from to build up that map. And that is where camera networks on Earth come in. I'm going to focus on the Australian Desert Fireball network to set this up, just because that's where I did my PhD out in Australia with these guys, and they do an amazing job. But I'll also flag that there are loads of camera networks. I think the Finnish camera network is here. There's the Czech network, the French network, Fripon. There's networks in Canada. There's basically networks all around the world doing very similar things. But yeah, I'll focus on the Australian Desert Fireball network to kind of give you an idea about what the plan is. The idea here is to set up autonomous digital cameras or video cameras or whatever you want that image the entire night sky all the time. Our systems are just off-the-shelf digital cameras with a fisheye lens. They take 30-second images. They're relatively quick to set up, and we set up several cameras all around Australia. the reason we picked Australia is it has a few environmental factors that make fireball imaging and meteorite hunting really easy. The first is the weather is gorgeous. There's like 90% of its days are clear sky, sunny, and it also has zero light pollution, particularly in the outback. So you get absolutely stunning night skies like this, where the sky is literally ablaze with colors and stars, which is spectacular and really good for imaging fireballs. The other kind of thing is Australia's landscape is really good for meteorite hunting. It's mostly barren, lifeless red dirt. And so little black rocks like meteorites stick out like a sore thumb. And so it makes it very easy to find them. So the Australian Desert Fireball Network set up around 52 cameras with their sort of initial network, covering about 1 million square kilometers, a third of a continent, and imaging that night sky every 30 seconds, every night, to basically get fireballs like this. Each of our images has an embedded timing sequence, so we are able to determine with sub-millisecond precision exactly when the light turned on, when that meteoroid hit the top of the atmosphere, and how it decelerated as it came down through, and what its terminal velocity is when it finally slowed down and the light goes out and it's then just in free fall. These things are in the middle of nowhere and they make quite good purchase, so sometimes this is what you see all night, but most of the time we see gorgeous night skies and fireballs. We very quickly realized that putting 50 cameras out in the outback that take an image every 30 seconds basically results in 1,000 images plus per night, gigabytes of data times 52 cameras. That is not a manual job. You can't make grad students like me do that. So they very quickly decided to go for an automated pipeline, which on the onboard computer on the camera then goes through all the images with an event detection system, figures out what images have a fireball in it. If one camera sees it, it then talks to all its other cameras around it saying, hey, I saw a thing. Did you see the thing too? And if they all go, yeah, they'll do a quick orbit, a quick trajectory, and a quick model to see if anything may have come out the other end. And so it's almost too easy now. We just wake up in the morning saying, oh, hey, there's a fireball. It's dropped a meteorite. Go search here, which is really kind of nice. And it's been working really well. This fireball was seen from multiple cameras. They were able to get a really nice trajectory. It was good, this one, because it had a really steep trajectory, so it was nearly 90 degrees coming in. And it also slowed down a really good amount, so very likely to drop quite a substantial chunk. And it went probably into the best searching area you could imagine, slap bang into the middle of the biggest salt lake in Australia, Katitanda Lake Eyre. So again, white salt, black rock, good chance of getting this thing. And so the team then goes out. Katitanda is a sort of area of special significance for the local Aboriginal community. And they were lovely and got on board with the expedition and helped our team get out into the field. Because Katitanda, although it's a dry salt lake, there are treacherous parts, boggy bits. And so they helped us get safely out into the field, into the search area where we thought the meteorite had landed. The local Air Force even got involved, sent some of our researchers up to be an eye in the sky, trying to see the meteorite from the air. And again, the search terrain is amazing. You have this barren red to white landscape. And so little black rock should be really quite obvious out here. So we've got a really good chance of finding it. Unfortunately, they also had a severe weather warning coming in on the horizon as soon as they got out there, and it was going to be quite a substantial storm event. So they were in basically a race against the clock to get this thing. The plane sent this image to the ground team, and when you see that, you go like, that's it, that's the splash, that's where that thing hit the salt lake. Go there. Unfortunately, the plane's going very fast, so they didn't get a GPS lock very well. And then Phil and Rob on the ground were being sort of like frantically searching everywhere as the sort of weather report got worse and worse and worse, and sort of like feeling kind of a bit disappointed, a bit devastated that, hey, we might not get this thing, we might have to evacuate. And then I don't really know how we managed this, but believe it or not, the meteorite is in this image. And Phil somehow managed to see it from the ground, ran over, started digging with his bare hands into this thick, congealed, salty mud, about 1/2 meter down, and with a sort of like glooping, suctioning sound, pulled out.
It's an iron meteorite, mate.
Oh my gosh!
It's not an iron meteorite. It was actually a H5 ordinary chondrite, but it was a meteorite nonetheless. Poor Phil's hands were so sore and tired from digging into this thick mud that just kept slooping back in. It felt much heavier to him. But anyway, this meteorite was the first meteorite recovered by the digital Australian Desert Fireball Network. It was recovered on New Year's Eve, believe it or not. It's a H5 ordinary chondrite. It's about 1.5 kilos. And the great thing about this is it was 5 years of work setting up this network, building the data pipeline, building the algorithms, installing the network. And so basically that was just an amazing feeling that all of the hard work from the whole team paid off in such spectacular fashion. And we have this space rock. And because we saw it come in, we have its orbit and we know where it came from in our solar system, and we can track it back to a specific asteroid. They've had several other finds. I'll just focus on this one because it fell on Halloween in Australia, and I'm not sure what it is about pagan holidays and Australian meteorite finds, but there seems to be a correlation there. This meteorite didn't fall into a salt lake, so it was actually landed in a dry field, and they recovered it within 2 days, which is amazing. No rainfall had fallen on this rock. It was just in a dry field. So there's going to be minerals in here that we don't normally see that get washed away very quickly. This is possibly the freshest meteorite you will ever see in your whole life, except one, which I'll come to later. But kind of the output of that success and imaging all these fireballs, we could generate this huge database, seeing where stuff comes from in our solar system. So this is all the orbits of all the fireballs that the Australian Desert Fireball Network saw over 5 years. Those teal dots are the meteoroids coming in to hit the Earth, which is that third rock from the sun there. And you can start seeing a picture about, there is some structure here. We're seeing where things are coming from. Like I really like here, I think it's either the Perseids or the Geminids are coming in to just sort of like nail the Earth just around here now. And built off this success, the Australian Research Council funded that project to go global. So the Desert Fireball Network could expand around the world to set up the Global Fireball Observatory. And the idea was to build on the success we had in Australia with finding meteorites successfully, using the kit, the technology we developed, and then send cameras out to international partners all around the world. And by that point, I'd got a postdoc position at the University of Glasgow, and in collaboration with Imperial College London, started to set up the UK branch, which we called the UKFall network. The aim of this Global Fireball Observatory, for context, is to send out these cameras all around the world to have 24-hour coverage of both hemispheres of our planet. So we're imaging the whole night sky, all night, every night. We're eventually going to cover 5% of the Earth's land surface, which is a bonkersly high value. And we should get around 5 meteorite falls per month across the whole Global Fireball Observatory. That will translate to about 300 meteorites falls visualized over the 5-year project, which statistically will give us one of every single meteorite type, including rare stuff like Martians, including rare stuff like lunar meteorites, and maybe even a comet. And in each case, we'll be able to track it back into space, figure out its orbit. And so it's basically like a reverse sample return mission. But instead of having to send a probe to an asteroid and bring it back, we wait for a bit of that asteroid to come to us. The UK Fireball Network started getting set up around 5 years ago. And obviously, we immediately had some challenges that maybe Australia didn't have. So as opposed to the glorious sunshine all the time, we have these grey, overbearing clouds in the sky. So our imaging is a lot poorer. But also our searching terrain is a lot more challenging. We have the boggy, like marshlands of Scotland, as well as like the dark green deciduous forests, fields with crops, rather than the sort of barren, lifeless red dirt of Australia. So finding meteorites is going to be a lot harder in the UK, but we also have quite a few advantages that Australia doesn't have. And the biggest one is you guys. We have way more people here and people that see meteorites fall and potentially see where they land. And in the UK, we've had quite a good heritage of recovering meteorites where we've seen them to fall. The last one in Scotland was over 100 years ago in 1917. It fell in the village of Strathmore. It was an airburst meteorite, so it split into 4 fragments, one of which absolutely nailed this woman's house and made a hole in the roof. And possibly the most interesting thing about this story, is, apart from like meteorite, is that this is probably one of the first examples of fake news in the modern media. And the reason for that is this meteorite fell on the 3rd of December, and it took a few days for the news crews to get up there. And so while there was a hole in the roof, in Scotland, you don't really want to have an open skylight because it rains a lot. So they'd fixed their roof by the time the news crews got there. Not to be dissuaded, the journalist took 2 images and then inked in where he thought the hole should be. So it's, yeah, so this image is a fabrication, but sort of shows you sort of like the determination of some journalists, which I found quite funny. The Glutton Meteorite was the last one to be found in the UK as a whole over 30 years ago in 1991. It was an ordinary chondrite found in the village of Glutton, right next to a chap called Arthur Pettifor, who was tending to his onions when this thing landed next to him. And he gave an amazing interview where they asked him, like, oh, weren't you concerned that it nearly hit you? And he said, oh, no, I was more worried that it narrowly missed my greenhouse. And having just purchased a greenhouse myself, I know how he feels. So we have got a good heritage of recovering meteorites, but we're not doing as well as we should be. Across the UK, on average, we should get 1 meteorite fall per year. And we haven't had one for 30. So we're batting way below our average. And that's where camera networks can come into their own to try and improve those statistics. So the UK Fireball network, we started to set it up in the UK. This is the light pollution map of the UK. And we want to stay away from the horrible red, white areas of London, Manchester, Glasgow, and stick in the sort of nice, clear, dark sky parks, sort of blue and clear regions of northern Scotland, the sort of north of England, Wales, and Cornwall. We also have a big advantage over Australia, that they needed 52 cameras to cover a third of it, and we only need 12 to cover the whole thing. We've currently installed 6 cameras covering sort of like most of England, most of Wales, and the southern part of Scotland. We've got plans to install a few more to sort of finish it off. We've had a bit of a hiccup, as you may understand, from the current COVID situation about getting cameras delivered and getting funding. But hopefully that will resolve itself in the near future. And I'd just like to say as well, I know I've been ragging on the UK weather system, but when it does go clear, we get some absolutely cracking views of the night sky that you can get some really nice images of fireballs. And so this is our camera network for the UK Fireball network. It's just placed on people's roofs, placed in the open air. We've got quite a good system because all of ours are powered by the mains and powered by local Wi-Fi, so they're all connected at all times, and we can get to them really easily. We don't have to drive for a week into the outback to go fix our cameras. If one of them goes offline, we can just drive down to sort of troubleshoot it. And this is a kind of a day in the night of one of our cameras. Okay, you can see sort of we get some cloud cover. You can see some flashes from local cars, a bit of light pollution from the nearby cities, some aeroplanes going overhead. But when the sky eventually clears, when it clears, you start seeing some really nice stars, able to calibrate your images. And if a fireball came through now, we'd pick it up and be able to see it. And so this is one of the first fireballs we managed to capture from that camera, despite the light pollution of being near London. We got this gorgeous image of this fireball. However, when we were starting to set this camera network up, we realized very quickly we weren't the only gig in town. There is a whole bunch of awesome folks up and down the country who've been doing this and been in this game a lot longer than we have. So there's the System for Capture of Asteroid and Meteorite Paths, or SCAMP network. They use video cameras to image the whole sky. It's based off the heritage of the Frippon network from France. And they have cameras mostly focused in the south of England, but sort of, again, like us, migrating their way north to get complete coverage of the UK. Like I said, it's based off the heritage of the Frippon camera network, which is started in France and is slowly advancing around Europe, and it will eventually have complete coverage of the entirety of Europe, which is awesome. And possibly the best bit about the Frippon network, aside from the awesome science they do, is it's, I think, the best acronym combo I've ever heard. So if anyone's familiar with their French, Frippon means mischievous small child, and SCAMP, the equivalent of the UK equivalent of that network, means mischievous small child in English. So when whoever came up with that deserves a medal. That's just brilliant. Their cameras are video cameras, so you get sort of like real-time footage. I'll just play that video again. You see the fireball in the bottom left, sorry, bottom right of this video coming through. So you get a really nice image of these fireballs using their cameras. There is also the UK Meteor Observation Network, and they use narrow-angle CCTV cameras to image the night sky. Their cameras are a lot more sensitive because they're designed to look for meteors, so those small flashes of light from sand-sized particles. And they do a fantastic job of calculating orbits and trajectories from those. But they also pick up fireballs. There's Nematode, there's the Global Meteor Network, there's All Sky 7, there's probably loads of others that I haven't mentioned. Basically, there's a whole bunch of folks doing amazing observational work, amazing astronomy, looking at the night sky, taking images with the express aim of imaging fireballs and calculating where meteorites that come from them may have landed on the UK. And so we were kind of thinking as we started talking to each other, getting to know each other, it's like, hey, we're all trying to do the same thing. Why don't we work together? And that's why we set up the UK Fireball Alliance. It's been led by a chap called Jim Rowe, who's done an awesome job bringing us all together under this umbrella of the UKFall or UK Fireball Alliance. This brings the professional networks of SCAMP, Frippon, and the UK Fireball Network, the Global Fireball Observatory, as well as amateur networks like UKMON, interested researchers that study extraterrestrial materials from up and down the country, from universities, as well as curatorial facilities like the Natural History Museum, National Museum of Wales, the Hunterian Museum, everyone who is basically interested in recovering meteorites, all banding together with the same goal. And we have a load of kit aimed at the sky now. So we've got really good coverage of what's flying around out there. Jim has done an amazing job getting us all talking to each other, getting all the data captured by different systems, different methodologies to be translated between camera networks, between models, between algorithms. In record time, we can turn around these things in less than a day. Which is fantastic and testament to the hard work Jim's put in. And some of the events we've seen with UKFall, we saw a Belgian Fireball on the 15th of Feb 2019. And this was cool because I didn't realize we would capture things over the continent, and I didn't think our field of view was that like far. But yeah, we were capturing stuff flying over Belgium. We caught it on one of our southern cameras. And if you're anything like me, you're like, wow, that fireball's really bright. And no, this is the moon. The fireball is actually this little thing over here, and I'm as disappointed as you are when I saw this image for the first time. I was like, whoa, that's so bright. Oh, no, it's over here, going behind this tree. But again, really cool that we saw this thing. Last year, on the 16th of Feb 2020, we got very excited when UKMON observed this fireball. We got it on a couple of cameras. Frippon and SCAMP got it on a few cameras. A few other networks gave us some data too. We sort of tested our data sharing algorithms. Yeah, several cameras caught this thing. And the great thing is we modeled it and we got a really nice orbit for this thing. And our model predicted that about 10 grams of material might have survived the fireball and landed on Earth. And we were like, fantastic, 10 grams. That's like, whoa, maybe about the size of sort of 5 centimeters or so. We could go search for that. We could go get it. Where did it go? And then we realized there was one small problem, that it went directly into the North Sea. So that's sleeping with the fishes. But it was great, sort of great opportunity in many respects to test our sort of like data sharing, how UKFall will work. So we're ready for the big one. And what's been nice in this sort of like data sharing, data testing with the fireballs we've seen over the last year or so is we're getting pretty close. All our data sets are starting to line up. All our numbers are coming out consistently, which is really great to see. And so we're ready for when it happens for real. And then that's where it gets really exciting because last week on the 28th of Feb at 9:54, I'll just play that video again because it's great. This fireball blazed across the UK skies just north of Cheltenham, fragmenting up several times as it went. Caught by literally every camera network of the UK Fireball Alliance. We got the data shared between each other in record time, very quickly realized that probably something fell out of this and there'd be stuff on the ground. got the news out there. Ashley King from the Natural History Museum, Richard from UKFall got on the TV, told people probably there's a really good chance that something's on the deck. It was also seen by everyone, as far as I could tell. It's the most widely reported meteorite ever. It broke the world record, which surprised me a lot because Chelyabinsk in Russia is a thing, and that was huge. But this fireball in the UK got reported by more people than that. So it's spectacular, seen from everywhere from Ireland through to the Netherlands, up and down the UK. We were able to really rapidly get its trajectory. It was really steep, which meant the strewn field would be really quite good. And this is kind of what our rough initial estimates were. Unfortunately, we're actually weirdly a bit delayed in getting a tight strewn field because of some unforeseen circumstances. The Frippon camera network guys, they'd seen their own fireball the day before us, and they were already in the field trying to find their meteorite in France. So getting access to their models to figure out the strewn field and where this thing landed was challenging. And also in Australia, because they followed a zero COVID policy, there was a public holiday, and the person who runs the dark flight model and the strewn field model was on holiday. He was out of signal reach, windsurfing somewhere. So we didn't get it quite as, we were delayed by 24 hours, which is still rapid response. But I guess the key thing to note here is slap bang in the middle of our estimated strewn field is the town of Winchcombe. And it's thanks to sort of like the UKFall initiative and the folks getting on the telly, telling people about this fireball that probably dropped a meteorite, that we were able to recover the splat. So the Wilcock family found this meteorite in their driveway, shattered into a million pieces. Their daughter, the night before, around 10 o'clock, heard it come in, heard the crack as it hit the driveway, which is amazing. However, initially, because it was dark outside, they just thought maybe something had fallen off the mantelpiece, but couldn't see anything amiss. And it wasn't until the next day that they looked outside and saw this pile of cinders, what looks like, or a pile of charcoal, splattered across their drive and across their lawn. It made a little dent, actually, like a few centimeter divot. And they initially thought maybe someone's playing a prank, maybe someone's throwing some charcoal at their house, or maybe the car's backfired somehow. But sort of very cleverly, they realized sort of quite quickly that there are very few things that this could actually be. And the most likely thing actually in this case is it's a meteorite. So they saw then on the news, sent their images in to the Natural History Museum, and then Richard Greenwood of the Open University saw this pile of dust and got really, really excited, going, "Oh my God, I think that's it. That's the meteorite. Go get it. Why hasn't anyone gone to get it? Oh, I'm in the area. I'll go get it." So he like ran out into the field, had a lovely chat with the family. They had already collected it up into a sterile bag, which is amazing and exactly what they should have done. And so remarkably, this whole thing got collected from falling out of the atmosphere to being in a safe environment within 12 hours. So it is the most fresh, pristine space rock you will ever see. And because of that recovery, because of the type of meteorite it is, there are now minerals inside here that normally degrade really quickly. If they're exposed to water, if they're exposed to rainfall, they just wash away immediately. The fact that the Wilcock family managed to get this safe so fast means that there are minerals in this that we never normally get to study. And this sample rivals that of the sample return missions like OSIRIS-REx and Hayabusa 2 in its freshness. And because we have its orbit, it's essentially the same deal, but at a fraction of the cost. We spent a few more days in and around this area trying to hoover up as much of this thing as we can. I personally spent about 6 hours with my head in their drive with a pair of tweezers, picking out the millimeter fragments and putting them into a bag, and then sort of like scouring through the garden and finding fragments in between the grass, finding them in the flower bed, just making sure we got as much of this material as we can. The meteorite we got from this driveway was about 300 grams in total. And from some preliminary analysis, it looks like it's a really rare type. It's called a CM chondrite, or a carbonaceous chondrite. which ironically is the exact same type of asteroid that Hayabusa 2 and OSIRIS-REx have gone to sample. So basically the equivalent of what we went to do with OSIRIS-REx and Hayabusa 2 just landed on a driveway in Winchcombe. And by this time, we'd then got a decent strewn field. And it was really good. I won't show it because it also shows where the strewn field is, and I don't want people to be breaking lockdown regulations to go search in this area. But we decided as an academic community that because this meteorite we've got is so rare, because it's such a once in a generation event, we should try and get a crack team into the field to search for more fragments. And so folks from the University of Manchester, University of Glasgow, Open University, Naturalist Museum, Imperial College, Plymouth University went through a literal mountain of paperwork to ensure that we could get our staff into the field in a safe manner, socially distanced, within government guideline regulations for the sort of COVID lockdown. And we managed to get a small team into the field to search the local area and search the strewn field. This is Ashley showing us some bits that were recovered from the driveway, so we knew what we were looking for. And who knew showing a freshly fallen meteorite, the first in 30 years, to someone has the same reaction as a proposal when you're a planetary scientist. That was news to all of us. And then we started our search along the strewn field. The way we do it is essentially it's like body searching. The same technique applies. You stretch out in a line about sort of one person every 3 to 4 meters, and then you just walk across the fields, walk across the landscape, looking down at the ground to try and find little black rocks. What I should say is what was really lovely about this whole experience and this whole expedition is talking to the landowners, talking to the folks in the area. They were just so lovely, so welcoming, so responsible, letting us get onto their land, onto their property to look for this thing in a safe, secure manner. We wouldn't have had the success we did without their sort of help and support. We also didn't know at the time exactly how many little black things there are in the UK countryside that look deceptively like meteorite fusion crust, that sort of glassy outer layer that meteorites have as they've burnt up through the atmosphere. So we got very excited on several occasions looking at sheep poo, as well as the dew on a spider web early in the morning over a hole gives that shiny glassy glint of a meteorite fusion crust, which I never expected to see. And then on the Saturday, after a lot of the groups had decided to go home, the Glasgow team stayed out for a few more days, and this was the result. We found a little bit of it in a field. It was in fact my girlfriend that found it, Mira Ihaz, and as we were sort of walking along in our search line, she just kind of stopped dead, like looked down, looked at me and sort of cocked her head and was like, could this be, is this it? And I sort of walked over, and as I kind of got closer, just realized very quickly, no, God, yes, this is it, this for real, like this is the meteorite. You can see its gorgeous fusion crust. You can see the flow lines as it's flowing through the atmosphere, and bits of it have just dropleted off. And it had embedded itself into the sheep paddock intact. And so, yeah, it was a really gorgeous piece. We spent some time excavating it, sort of taking images. And what was great about this is it shows that not only can we find meteorites when they hit people's driveways, if we're not lucky and they don't hit people's driveways, and we get the meteorite because members of the public tell us that they've been hit by one, we can go out into a field, into the landscape, search these areas and recover fresh meteorite falls in the UK, which is great and such a relief to know that all our hard work over the last 5 years to a decade building UKFall and the UK Fireball Alliance works. And I would also like to note we did some sophisticated preliminary analysis to weigh the thing, because I initially estimated about 50 grams and my girlfriend didn't believe me. So it actually weighs the same as 2 chocolate bars, which is around 100 grams. So we have a more revised estimate. I'm sure the Naturalist Museum has a better estimate now. They've got it into their labs. And now the kind of real fun begins in many ways. We have this beautiful carbonaceous chondrite that's only been exposed to our atmosphere for about 12 hours. It's comparable to sample return missions in terms of its pristine nature. And we saw its fireball, so we have its orbit. We can track it back into our solar system. Its orbit's just here. This is Mars's orbit. This is Jupiter's. So you can see the orbit of this thing before it hit us stretches out just on the inside of Jupiter's orbit, which is really cool and will give us the geological context we need to interpret this rock. What's going to happen now is it's currently at the Natural History Museum being carefully curated, divvied up, weighed, imaged, looked after, and soon it will be distributed to scientists around the UK that study this kind of material, that study extraterrestrial rocks. And they're going to do what the UK scientific community does best in analysing this, dissecting it, shooting all the lasers, all the X-rays, all the electrons, tearing little bits of it apart an atom at a time to really dissect it, figure out what's going on inside this rock, figure out how it formed, what its history is. And there's some really exciting questions we're probably going to learn from this rock because it is so special, because it is unique. It's probably going to go down as the most significant event to happen in planetary science in the UK ever. That's kind of how important it is. So I'm really looking forward to sort of getting this into our lab, getting it into labs around the country, and really sort of throwing the kitchen sink at this thing to understand how it formed, and by extension, how planets form, how asteroids evolve, how our solar system evolved, and potentially even how life emerged on Earth. Because potentially meteorites like this hitting our early forming planet gave it the ingredients, the organic compounds, the amino acids, the water to produce a nice habitable world in which life could develop and ultimately lead to us. And so this has just been a great experience, a great feeling, wonderful sort of validation of all the work loads of people have put in all around the world to make this happen. But that's not the end. I really hope this is just the beginning. Because like I said, one meteorite should fall every year. So I think this is the first of many, not the end of the story. And what I'm hoping in the future is that next time we'll be able to bring you along and you can help. It was unfortunate that this meteorite fall happened during COVID lockdown. So the only people we could safely get in the field was a very small group. In the future, when hopefully we can go out in public and see each other again, and we have the next fireball, because there will be another fireball that drops meteorites in the UK, we would dearly love to have a suite of volunteers. You can sign up to the UKFall mailing list or the UK Fireball Network mailing list as a volunteer, to be able to come with us, to turn up in a field when we've seen a fireball to help us in the search effort so we can cover more ground. In the meantime, though, you can also download our free app called Fireballs in the Sky. It's available for Android and iOS. If anything, it's just a really lovely star map, but at the same time, if you see a fireball in the sky, you can report it using this app and give us your trajectory estimate. So you basically uses the inbuilt GPS of your phone. You point it where you saw the fireball start, click, point it where you saw the fireball end and click. You can tell us what color it was it green, was it orange? You can tell us, did it fragment, how long did it last? And did you hear a sound? You send that report to us. That goes into our database. If multiple people see the same event, it gets flagged, and we can use those observations that you make with your smartphone, believe it or not, in our data pipeline to help us refine our orbits, to help us to refine our trajectories and figure out where these things are landing and hopefully go get them. And with that, I'll end this talk. Thank you so much again for having me. It's been a utterly crazy 2 weeks in the best possible way, and I would be more than happy to answer any questions you have.